Imagine a star that is so massive and dense that it bends the fabric of space and time around it, creating a gravitational well so deep that nothing can escape from it, not even light. Now imagine another star that is similar to the first one, but it does not have a point of no return at its core. Instead, it has a tiny ball of matter that is compressed to the smallest possible scale, allowing some light to escape from it, but very dimly and distortedly. These are not science fiction scenarios. These are two of the most extreme and mysterious objects in the universe: black holes and dark stars. In a previous episode, we covered this news story where scientists claimed they found dark stars using the James Webb Telescope. Based on your feedback on that video, we decided to make this episode, in which we will explore three main topics: why people are confused between dark stars and black holes, what the structure and properties of dark stars are, and why we study these objects. Let's begin. Dark stars and black holes are very extreme objects that have a very high escape velocity, which is the speed needed to escape their gravitational pull. For example, if you want to launch a rocket from Earth, you need to reach a speed of about 11 kilometers per second, or 40,000 kilometers per hour. That's pretty fast, right? But if you want to launch a rocket from a black hole or a dark star, you need to reach a speed that is close to or greater than the speed of light, which is about 300,000 kilometers per second, or 1 billion kilometers per hour. That's impossible, right? Both dark stars and black holes are also surrounded by an event horizon, which is the point of no return for anything that falls into them. Once you cross the event horizon, you can never come back, no matter how fast you go. The event horizon is like a one-way door that leads to a place of no return. The event horizon is also where things get really weird and counterintuitive. For example, if you watch someone falling into a black hole or a dark star from a safe distance, you will see them slowing down and fading away as they approach the event horizon. But if you are the one falling into a black hole or a dark star, you will feel nothing unusual until you reach the event horizon, and then you will be torn apart by the extreme gravity. So far, dark stars and black holes sound very similar, right? But they are not exactly the same. There are some key differences between them that make them distinct objects. The main difference is what happens at their core. A black hole has a singularity at its core, which is a point of infinite density and curvature. It is where all the laws of physics break down, and we have no idea what happens there. A dark star does not have a singularity at its core. Instead, it has a Planck core, which is a very dense core of matter that is compressed to the smallest possible scale, called the Planck length. A Planck core is where quantum effects dominate over gravity, and we have some idea what happens there. More on that later. Another difference is how much light can escape from them. A black hole does not let any light escape from it due to its escape velocity being equal to or greater than the speed of light. A dark star lets some light escape from it due to its escape velocity being slightly less than the speed of light. However, the light that escapes from a dark star is very redshifted due to the extreme gravity. A third difference is how big they are. A black hole is very compact and has a very small event horizon compared to its mass. A dark star is very large and has a very large event horizon compared to its mass. This means that a black hole has less space inside its event horizon than a dark star with the same mass. These are some of the main differences between dark stars and black holes that make them unique objects in the universe. But how do we know about these differences? And how can we study these objects if they are so hard to detect? So now we know that dark stars are hypothetical objects that have a very dense core of matter that is compressed to the smallest possible scale. This core is called a Planck core. A Planck core is where quantum effects dominate over gravity, and we have some idea what happens there. It is named after the Planck length, which is the smallest possible length that can be measured in physics. The Planck length is about 10 to the power of minus 35 meters, which is much smaller than an atom or even a proton. To give you an idea of how small it is, imagine a grain of sand. Now imagine that you divide it into 1 billion pieces. Then you take one of those pieces and divide it into another 1 billion pieces. Then you take one of those pieces and divide it into another 1 billion pieces. You would have to repeat this process about 25 times to get to Planck's length. This core is a ball of matter that has a radius of about 1 Planck length and a mass of about 1 solar mass. This means that it is extremely dense and has a very high pressure and temperature. The pressure and temperature are so high that they overcome the nuclear forces that hold atoms together and create new forms of matter that we do not understand yet. The temperature is also so high that it creates a lot of radiation that escapes from the core. The radiation that escapes from the Planck core is what makes dark stars different from black holes. Black holes do not let any radiation escape from them due to their escape velocity being equal to or greater than the speed of light. Dark stars let some radiation escape from them due to their escape velocity being slightly less than the speed of light. However, the radiation that escapes from dark stars is very redshifted due to the extreme gravity. This redshift means that the wavelength of radiation gets stretched as it moves away from a source of gravity. This makes the radiation appear redder and dimmer than it actually is. The redshifted radiation makes dark stars very faint and cold, which makes them invisible to most telescopes. The surface temperature of a dark star is about 10 to the power of -7 kelvins, which is much colder than the cosmic microwave background radiation, which is about 2.7 kelvins. Additionally, dark stars are very large and have a very large event horizon compared to their mass. The event horizon is the boundary that separates the inside and outside of a dark star. Anything that crosses the event horizon is doomed to fall into the Planck core and never come back. The size of the event horizon depends on the mass of the dark star. The more massive the dark star, the larger the event horizon. These are some of the main features and phenomena associated with dark stars that make them unique objects in the universe. Dark stars are one of the possible solutions to the problem of dark matter, which is a mysterious form of matter that does not interact with light or normal matter, but has a gravitational effect on the universe. Dark matter makes up about 85% of the matter in the universe, but we do not know what it is or where it comes from. Some scientists have proposed that dark stars are made of dark matter and that they were the first stars to form in the early universe, before normal stars. If this is true, then dark stars could help us understand the origin and nature of dark matter, as well as the evolution of the universe. Dark stars are also special and important because they challenge our understanding of physics and astronomy. They are very different from normal stars, as they do not have nuclear fusion or a singularity at their core. But how can we find and study dark stars if they are so faint and cold? There are some possible ways to detect them indirectly, such as gravitational lensing, gravitational waves, or gamma-ray bursts. These methods can help us find dark stars if they exist, but they are not very reliable or conclusive. We need more data and evidence to confirm or reject the existence of dark stars. We also need more advanced and sensitive telescopes, such as the James Webb Space Telescope, which has already captured some images that researchers claim contain candidates for dark stars. However, these images need further analysis and verification before we can claim that we have found dark stars. These are some of the reasons why we care about dark stars and what makes them so special and important. Thank you for watching this video. I hope you enjoyed it and learned something new. If you liked this video, please give it a thumbs up and share it with your friends. And if you want to see more videos like this, please subscribe to our channel and hit the bell icon to get notified when we upload new videos. And don't forget to leave your comments and questions below. We would love to hear from you. Until next time, stay curious and keep exploring.